Okay, so today we're going to go over waves. Now, being in a landlocked province, we don't get to see much in the way of serious waves around here. Okay, like maybe on a windy day, you see out on the lake, the lake's capping a little bit. Okay, those are wind-powered or wind-induced surface-going waves, and that's really the extent of what we know as landlubbers here in Alberta. Okay, but if you were to live on either coast, you might have a greater experience with waves and have a better understanding of them. Okay, so what we're going to look at today are the two kinds of waves. Okay, we'll look at a few videos here and there, what waves look like, how they travel, all of that kind of stuff. Okay, as just an introduction to the last half of this unit. Okay, so the two types of waves we're going to look at are transverse and longitudinal, not longitudinal. That's lines on a map that go east and west. Okay, longitudinal are a type of wave. Okay, and then understand how waves are created and propagated. Right? Generally, how do you make a wave? What do you have to do? Even philosophically, sometimes people are like, well, that person makes waves. Okay, it's not like real waves, but they're causing a what generally? Starts with D. A disturbance. Yeah, okay, they're making waves, they're causing some kind of disturbance. That's what a wave is. Okay? A wave is a traveling disturbance. It is created by something disturbing something else, and then the energy travels away from the point of disturbance. If you've ever thrown a rock into a lake, you have seen this. Okay? The lake hits the water, and the waves travel outward in concentric circles from the point where the rock hit the water. It disturbed the water. Because the water is a polar molecule, it actually oscillates up and down a little bit. If you've ever seen that happen in slow motion, you see the water go down, and then you see some water shoot back up, okay? And that water splashes down. It's actually the water oscillating up and down due to the disturbance. It's why throwing a rock in a lake makes more than one wave, okay? If water wasn't a polar molecule, you'd only get one wave. Okay, but it is, so it oscillates up and down because it holds onto itself. Okay, so what we're seeing there is the energy travel outwards. Now here's the thing about waves. Waves are not matter. They travel through it, they disturb it, but waves themselves are not matter, which means they're not bound by the same rules as all the things we've talked about up until now. Okay? If I want to change the speed of an object that is matter, that object has to accelerate. That takes time. Waves can change speed instantaneously. They don't have to accelerate. They just change like that. Okay? Because they're energy, not matter. They're traveling through matter, they're disturbing matter, but they're energy. Okay? And we see their effect, the effect of that energy, on the matter itself. Or, if they're sound waves, we hear it instead. Okay? Right now, you can hear my voice because my vocal cords are moving back and forth, and they're disturbing the air around them, and that disturbance is projected out to you. Okay? The air molecules are vibrating back and forth. They hit your eardrum vibrates back and forth, just like the air was, and then your brain translates that as sound. Right? Everybody following me so far? Okay, so that's the part about waves that people generally struggle with. Okay, a wave is not matter. Okay, we can see the effect of a wave on matter, but the wave itself is energy, which is why it can do weird things. Okay, it's why it can pass through a wall or a window or a door. Okay, and not be like overly affected by it. All right. Okay, and then we're going to talk about parts of the wave, properties of the wave, okay, things like that. All right, so a wave is a traveling disturbance. That is the definition of a wave. Okay. Now, a wave is also evidence of an oscillation. Simple harmonic motion. So a lot of the same terms are going to apply. Waves have frequencies, periods, okay? Amplitudes, all that stuff that we've talked about with simple harmonic motion, those same properties will apply to a wave along with a couple of new things, okay? Now, waves, with the exception of light, require a medium in which to propagate. Okay, that means they need something to travel through. Light is the exception. Light can travel through the vacuum of space because of the wave-particle duality or nature of light. Light is both a wave and a particle, so it can make its own medium to travel through the vacuum of space. That is the exception. We are going to talk about mostly classical waves, okay, in this. Okay, we will use light occasionally, but we're going to talk about waves that actually need a medium to travel in. Okay, now, way back in the 80s, this movie came out. It's called Alien. You've probably seen some of its, children, grandchildren. Okay, the franchise has been kind of beat to death lately. Okay, but the original Alien movie came out, and the movie poster, okay, had the picture of the alien egg on it. Okay, the little green light coming out the top, supposed to be kind of suspicious. The tagline was, "In space, no one can hear you scream." Which is not only a cool way to introduce a movie, but it's also true. In space, no one can hear you scream. Why not? What's in space?
I was just going to say, it's like sound can't travel through space.
Right.
There's no waves.
Well, not so much that there's no waves. Light waves can travel through space, but no, sound waves can't because there's nothing to propagate them. Right now, you can hear me because of the effect my vocal cords are having on the air in this room. Okay? I make the air vibrate. Okay? The little particles of air move back and forth, and that wave travels through the air and meets up with your ears. I can't do that in space because there's no matter out there. It's a vacuum. Right? So if you are out in space, okay, and let's say you're in your spacesuit, so you're alive, but something's really, really terribly wrong, so you're screaming your head off, which, by the way, astronauts are super calm, cool, and collected. They wouldn't do that. Okay? But let's say you're out there and you're screaming. If your radio's not working, you're the only one who can hear you scream. The air inside your suit, okay, will carry the sound around and bounce off all the parts and hurt your ears by screaming. But even if your partner is right next to you, all they're going to see is you doing this. They won't be able to hear it unless they grab your helmet and put the faceplates together. Now can they hear you? At which point they'll go, "Jeez," and pull you away again because you're screaming, and that's going to be annoying. Okay? Why is it when you put the faceplates together that they can hear you? Right. The sound it's going to make your faceplate vibrate. Okay? If you ever, you guys probably didn't do this because you had cell phones from an early age, but when I was a kid, we used to put two soup cans together with a string, and you could talk through the soup can. Because when you talked into the soup can, the bottom of the soup can would pick up the vibration, which would be transferred through the string as a wave to the other soup can. Okay? And the bottom of that soup can would vibrate, and you'd be able to hear on the other end. Okay? We were easily entertained. Okay? We didn't have phones. All right? That was our phone. That works in the same way as putting the two faceplates together. As soon as the two faceplates are put together, now there's matter that the sound can travel to the other suit. Okay? Both faceplates will vibrate, and then they'll transfer that vibration to the air, and the person on the other side will be able to hear you. It's kind of like putting your ear up against a door to hear a conversation on the other side. Okay? You're reducing the amount of air that the sound has to travel through by putting your ear directly on the door. All right? Sort of make sense? Okay, so waves require a medium in which to travel. There has to be some particles that can be disturbed by the energy and carry that energy away. Okay, now, how do we know a wave is energy? If you have energy, you can do work. Can waves do work? I've seen lots of evidence. If you've ever watched the news, when there's a tidal wave, okay, waves can do a lot of work. Okay, they carry a lot of energy. Okay, but in a simple example, like this one here, we have a motorboat who passes by, okay, a fisherman who's just sitting in his boat. Right? So as the motorboat goes by, it pushes the water down and out. Okay, well that water comes back up and it oscillates up and down, and then that energy travels away from the disturbance. The motorboat is the disturbance. Okay, when that wave gets to this boat, will it lift up the boat? Okay, if it can lift up the boat, that's work. It takes work to lift the boat. Okay, so the waves definitely carry energy. And you wouldn't be able to hear anything if waves didn't carry energy, because it takes work to make your eardrum vibrate back and forth. Okay, so waves carry energy and can do work. All right, so that's something else to know. Okay, waves obviously require a medium in which to propagate. Water, air, okay, wood, concrete, they can all carry waves. Okay, and they carry energy from place to place. All right, everybody okay with that? Okay, so there's two kinds of waves. I'm actually going to grab a slinky here just so you can kind of see what these look like. All right, so transverse waves are like the diagram that you see here. The disturbance is perpendicular or transverse to the direction the wave will travel. Okay, that generally makes a sinusoidal wave pattern, okay, in the medium in which the wave is traveling. Okay, now the big thing to remember here is this. A wave travels through a medium. The medium does not move with it. Okay? Like, this is the part that we get wrong all the time. We see like a tidal wave or something like that, and we see the ocean going along with the wave, which is not accurate. Okay? If waves that were always crashing on the shore meant the water was going that way, well, eventually there'd be a big hole in the middle of the ocean and all the land would be flooded because all the water would go onto the land. Okay, is that what happens? It's not. Okay, so a wave just makes the water go up and down. The water doesn't go left to right. The wave does. It passes through the water and the water just goes up and down and then comes back down. Okay, now here's where you're probably thinking, yeah, but Coderre, in a tidal wave, the water goes in and it swallows everything up and it's destruction and all that bad stuff. The water goes in, yes, but not in the way you think. Okay, science fiction has kind of done a really bad job of showing what a tidal wave looks like. Okay, it's always this giant white maw that's just coming in, like the ocean just reaches out like a big hand and pulls everything in. That's not what happens. Yes, you'd see the big curling wave, but the one thing science fiction has done well is show the shock wave that could precede a tidal wave. When the wave runs out of water, and it does, it gets to the shore and then there's no more ocean, the wave passes from the water into the air. So if you were standing on the shore, not a good idea by the way, when a tidal wave is approaching, okay, you would actually feel a big gust of wind, okay, right before you're swallowed up by the tidal wave, because you'd see the wall of water and then you'd feel the gust of wind. And at that point, what's happened is the wave energy has left the water, moved into the air, and now all the energy from the wave that was holding the water up is gone. So what's the water going to do? Fall. It's the splash from a tidal wave. That's the big problem. Okay? That's what we see. I'll show you a video of what a real tidal wave looks like. Okay? It just looks like the ocean just kind of comes in. Okay? It doesn't generally look like a big white maw coming in to destroy everything. You might see that out there, but it itself doesn't come in. All of a sudden, just the ocean just is bigger. Okay? It's actually that wave collapsing. Okay? And when you drop water, it spreads out. Okay? And that's what we see come in. Okay? So that would be a transverse wave, because obviously the water is displaced up and down. Okay, so some terminology here about waves, just so that we know what we're talking about. Okay? The amount of time it takes a wave to make a complete oscillation is still period. Okay, it's the time for one cycle, so it's still period. The number of waves per second, that's still frequency. It's still oscillations or cycles per second. So those terms still apply. Equilibrium position still applies. Amplitude still applies. It's the maximum distance from the resting position of the medium that the medium will achieve. Okay? And it's actually amplitude that really determines the energy of the wave. Because as you'll learn later, the speed of the wave is actually dictated by the medium it's traveling in. Okay? So you can't accelerate a wave. We talked about that earlier. Okay? The wave can travel at a certain speed in a certain medium. All right? Like, if I was to talk in this voice and then shout, do the waves travel any faster if I'm shouting? They don't. The sound in this room can travel at about 340 meters per second. And it doesn't matter whether I'm whispering or shouting. They all travel the same speed. Okay? It's like a gunshot at the track meet, right? When they fire the gun, if you're on the far end of the track, there's like, you can see the smoke and then you hear, okay, the sound of the shot later. It doesn't matter whether it's a shot, a shout, a whisper. That sound would take the same amount of time to get to you. Okay? So, but what is different is the amplitude. When I'm talking in this voice, the amplitude of my waves is not as great as when I shout. Okay? When I shout, my vocal cords move further. They don't make the sound travel faster, they just make the sound waves bigger. Okay? And they make your eardrum move further. Right? And we perceive that as a change in volume. That has to do with amplitude, not speed. Okay? All right. So, other terms that are new. Okay? Crests and troughs. Okay? These are the names given to the maximum amplitudes above equilibrium and below equilibrium. So, a crest is above equilibrium, a trough is below equilibrium. Maximum amplitude in either direction. Okay, equilibrium position, still a term that we know from before. And then wavelength. Okay, wavelength is the actual physical length of one cycle. Okay, we don't have really a comparison for that in simple harmonic motion. Okay, but for a wave, because we can sometimes see it, okay, the distance from any two equal points on the wave is one wavelength. All right, so I'm just going to diagram that here with this line. All right, so that line is one wavelength. Okay, in this initial situation, it's the distance from one crest to the next crest. Okay, but it's also, oddly enough, the distance from one trough to the next trough. Or any 2 points on the wave that are consecutive. Okay, so as this wave moves along, okay, the wavelength is always the distance between any two equal points on the wave. Okay, now this is usually the point where people are like, except for right here, Coderre. Okay, the next equilibrium position isn't a full wavelength away. Yes, it is. Two equal successive points on the wave. The wave in this equilibrium position is on its way up. Here, the wave is on its way down. So from this on its way down to the next on its way down are still one wavelength apart. Okay? Equal successive points on a wave are one wavelength apart. Okay? That's going to be measured in meters. Okay? Obviously, it's a distance, so it's going to be measured in meters. Now, this symbol right here, okay, this is what we use to represent wavelength. Okay? Because obviously we can't use L. L's already for length. Okay? So wavelength, we use the Greek letter L. That little symbol right there is lambda. Okay, the Greek letter L. You don't have to draw it as fancy as that. That's what it technically looks like. I'm good if you just do this. Okay, it's a long stick supported by a short stick. Okay, that's lambda. You can just draw it like that. You don't have to put the fancy little tails on it every time you draw it. Okay, you'll never see me do that. Okay, just like that. That's fair. Okay, so lambda stands for wavelength. Okay, got a couple of videos here I'm going to show you, okay, about wave. Okay, so I mean, obviously there's a lot of energy there, right? I mean, that's kind of the big point of today, is that waves are a traveling disturbance. They carry energy. Okay, they're going to have these parts. They're going to be influenced by these things. Okay, that's what we want to talk about today. All right, so those have all been transverse waves. Ocean waves are transverse waves. Okay, we haven't talked about the longitudinal ones yet. Okay, the principles are still the same. They just look different. Okay, so rather than having crests and troughs, longitudinal waves have compressions and rarefactions. Okay, so compressions are where it gets pushed together, and rarefactions are where it gets stretched apart. Okay, but the big thing with the longitudinal wave is the oscillation of the medium is back and forth, parallel to the direction the wave goes. In the transverse wave, the oscillation is up and down, perpendicular to the direction the wave travels. Put your phone in the pocket before you go. Okay, everybody with me there? Okay, so that's what this part here is showing. Okay, it's showing right here. This is the direction that it oscillates. It's back and forth. As a compression goes by, it would get pulled this way. As the rarefaction goes by, it gets pulled back the other way. But if we marked a spot on the slinky, that part would just go back and forth. Okay, it's not going to travel from A to B. Otherwise, obviously, I'd run out of slinky by making waves. Okay, it would have to go away from me, and it doesn't. All right, so kind of paused, you can see here on this slinky, there would be a compression, here would be a rarefaction, this would be one full wavelength, okay, from here to there. Okay, that's the length of one complete cycle in a longitudinal wave. Okay, and if we're watching the equilibrium position, okay, with a marked ring on the slinky, we would see it go out, we would see it come back past the equilibrium position, okay, but that's all it would ever do. Okay, questions there? All right, so as we were saying here, both transverse and longitudinal waves are periodic waves. Okay, so they have a period, frequency, wavelength, amplitude, okay, all of that stuff. They are a medium that is oscillating up and down. So the medium they're traveling through is exhibiting or experiencing simple harmonic motion. It is oscillating. Okay, waves are produced by simple harmonic motion. Right? When you throw a rock into the water oscillates up and down because of the disturbance. Okay, in an earthquake, okay, the earthquake waves make the Earth's crust move up and down, okay, and that's going to make any water on top of it move up and down. Okay, what do you have to worry about after an earthquake besides a tsunami? Might be hours or even days later. Starts with A. An aftershock. Okay? Aftershocks are reflections. Okay? So the earthquake causes a disruption in the Earth's crust, but remember, under the crust is the mantle, okay? That liquid layer of rock. Well, the waves, they travel both directions, out and in. So those waves can travel through the mantle, reflect off the other side of the Earth, bounce around a few times and come back. And when they come back, they're going to push on the crust again, creating an aftershock. Okay, so you do have to worry about the waves coming back to that area as a result of reflection. Okay. All right. Okay, so as we said, the length of one cycle is the wavelength, that's lambda. Okay, the amount of time it takes for that to happen is the period. The number of those that go by every second is the frequency. All right, now a super important thing that we need to know about waves, all waves. Once a wave is produced, its speed can change, its wavelength can change, its Amplitude can change, but its frequency will never change. Once a wave is produced, its frequency will remain the same. There is nothing you can do that will change the frequency of a wave after it's produced. Okay? I could make different waves with a different source and have them have a different frequency, but those are new waves. Once a wave is produced, its frequency will remain the same, cannot be changed. Okay? Here's kind of a prime example of that. If you've ever shown a light into water, okay, have you ever noticed how it kind of bends when it goes into the water? Okay, but if I do that with a laser pointer, okay, does the color of the laser change? Or does it stay like this red laser? Is it red in the air and the water? Totally is. Okay, the color of that laser is due to its frequency. Believe it or not, when that laser hits the water, it slows down. The light slows down. Okay? Light travels at different speeds, and all waves travel at different speeds in different media. That's why waves get taller as they approach the shore. We change the properties of the water. We make it shallow. That changes the speed. But the same number of waves will go by me every second as they did for that Coast Guard vessel that we watched go over the wave. Okay? Those waves have the same frequency in deep water as the waves in shallow water do. Because out in the deep ocean, they're traveling really fast and they're really long. When they get close to the shore, they're really short and really slow, but the same number of waves goes by every second. So the frequency of a wave doesn't ever change. I think I've said that a half a dozen times in the last 2 minutes. Okay? So it's super important. The frequency of a wave never changes. Okay, so just review of terminology here. Amplitude is the maximum excursion of a particle in the medium from its resting or equilibrium position. Amplitude measures the energy of the wave, okay, because it takes more energy to disturb it further. So greater amplitude, greater energy. Just like in a mass on a spring or in a pendulum, the further from equilibrium it goes, the more energy it has. The greater the amplitude, the more energy it will have. Okay. So this is the thing to remember about conservation of energy for a wave. Okay? Out in the deep ocean, the waves are traveling really fast. They got lots of kinetic energy. As they approach the shore and they get slowed down, they get taller. They convert the kinetic energy into potential energy. The energy is conserved, okay, as the wave travels. Okay, crests, troughs, we've kind of talked about those already. Okay, wavelength, remember lambda is the horizontal length of one cycle, one complete cycle. Okay, that is any two equal successive points on the wave, crest to crest, trough to trough, anywhere along the way. Okay, and this is just the same thing we talked about. Period is still the same thing. It's still the time for one complete wave to pass by you. Okay, frequency is the number of waves that go by every second. Period and frequency of a wave can never change once the wave is produced. Okay, here's another example. Anyone ever gone swimming and they have the music playing in the pool and you can hear it below the water? Other than the fact it sounds like you're underwater, can you still tell it's the same song? It's because the frequency of those sound waves hasn't changed. Okay? You still hear Like if it was a middle C or something and it was like 375 hertz, you'd hear 375 hertz above and below the water. Middle C would be middle C. Wouldn't matter above or below. Okay. All right, so they use a train analogy here as kind of going to the different properties of the wave. So the speed of the train is the speed of the waves. The length of one car is the wavelength. Okay, number of cars that go by every second is the frequency. Time for one car to go by is the period. Okay, now what I like to use is an example that's maybe a little closer to home. If you drive out here, okay, when you're coming into town, the speed limit goes from 100 to 80 and then to 60. All right, so what we're going to look at is the 100 to 80. So if I'm standing here, okay, and I'm watching cars go by, out here where the cars are traveling at 100 kilometers per hour, okay, I'm going to see 3 cars go by in 1 second, let's say. Okay, so I saw 3 cars go by. This is how far apart they were. Now, when they go into the next medium, or they go into the 80 kilometer an hour area, okay, this car gets to the 80 kilometers before the others, agreed? So it's got to slow down. So what happens to the distance between this car and this car when that one slows down? It gets smaller, right? This car catches up to that one, same here. So if I had another person sitting here, they would see those same 3 cars. But they're going to be closer together, traveling slower. But 3 cars are still going to go by them every second, just like for me out in the 100 kilometer an hour area. Okay? The same is true for waves. If I change the speed, I'm going to change the wavelength. Those two will always change together to make sure that frequency never changes. Okay? Frequency doesn't change because the other properties of the wave change instead. Okay? If you slow a wave down, then the wave has to get shorter. If you speed a wave up, then the wave has to get longer. Okay? So if, let's say that this went back out here to 100 again. Well, when this car gets to the 100, it's going to speed up. It's going to increase that distance between it and the car behind. Okay? And I'd be back to still 3 cars going by every second, but they'd be further apart again. Okay? There's the properties and behavior of waves that is super, super important to understand. Frequency never changes. I'm pretty sure that's like the 14th time I've said that. Okay? It is super, super important. Okay? Speed, wavelength, amplitude, those can change. Period and frequency cannot. Okay. If we had something oscillating, like a mass on a spring oscillating up and down, does it make a wave? Right? Like if I just drew and followed the pattern of the thing moving up and down, I'd make a wave. Because anything moving with simple harmonic motion is going to disturb the medium around it, whether that's air or water or what. Okay? It's going to disturb it, and that energy is going to travel outwards as a wave. Okay? Okay, so we're going to leave it there. It's almost perfect time. Tomorrow, okay, we're going to talk about the universal wave equation. Okay, and that's pretty simple to use. Okay, it's just V equals F times lambda, or lambda over period. Either one. Okay, that's what you're going to learn about tomorrow. You're going to do some practice questions from the workbook. Okay, that'll be the plan.